ואז זה כמו ממש משהו שלא פתרנו בכלל.
שאלה שלוש.
The last two lectures of this semester will be devoted to asymptotic analysis of integrals. And to begin with, let's start with, just to set the stage, let's start with simple problems and continue to more complicated scenarios. So first of all, suppose we have the integral sine t over t from 0 to 1, sine of xt dt, and I want to analyze this integral to find the asymptotics of this integral at x goes to 0. Okay? What should I do? Here the trick is very simple. As x goes to 0, the sine xt is very, very small. So I can write the simple expansion integral from 0 to 1 of 1 over t times, say, xt minus x cubed t cubed over 6 plus blah blah blah, right? And I will integrate it term by term. So the first integral is an integral over x because the t cancels out, and I have x, integral from 0 to 1 over nothing, it's over dx, so it's x. And then I have minus x cubed over 6, integral from 0 to 1 of on t squared dt, squared not cubed. And this is t cubed over 3. And I have contribution only from the upper bound, so I will get x, overall I get x minus x cubed over 18. Okay, and then the next term will be plus x to the fifth over who knows what. I think it ends up to be 600, and so on and so forth. That's the idea. Yes, I simply expand the sign for small x. This is what we did. Okay? A little bit, tiny bit more complicated. Let's ask now what is right? What is the asymptotic of that integral, again, as x goes to 0? So the point is that I want to find the asymptotic where, with respect, not with respect to something that is in the integral, but with respect to the boundary, right? Even though it doesn't matter because I can change variables here, and then the x will appear at the boundaries also. It's not such a big difference. So what do I do to deal with this integral? And I want it when x goes to 0. Okay, so what do I want to do first?
That's t to the 4th power?
Yeah, so that's t to the 4th power. Note that I can write it as an integral from 0 to infinity on e to the minus t to the 4th dt, minus the integral from 0 to x of e to the minus t to the 4th dt, right? Because I just and this term will be small when x goes to 0, right? Now, what is that?
The same integral.
Okay, so to understand what is that, let's define t to the 4 to be q. Therefore, so t is q to the 1/4, and dt is q to the minus 3/4 times dq times 1/4.
So it's the gamma function.
Exactly. So this integral I can write as the integral from q equals 0 to infinity over dq, and I have 1/4, and then I have q to the minus 3/4 times dq, times e to the minus q, and this is a gamma function of 1/4. You see, so what I obtained from this is gamma function of 1/4 divided by 1/4, and since gamma of z plus 1 is z gamma of z, and this is gamma of 5/4. Okay? Wait, no. Over 4, not over 1/4. I have 1/4 here, right? So it's over 4. So it's more transparently this. And that's gamma of 5/4 gamma of 4. Okay. So I'm done with that, and I have only to estimate this when x goes to 0. What can I do? So I have gamma of 5/4 minus, and now I have the integral from 0 to x over e to the minus t to the 4 dt. Okay? However, x is very small, which implies that t is very small. And if t is small, I can expand the exponent. That's a trick here. So I can write the exponent as 1 minus t to the 4 minus t to the 4 plus 1/2 t to the 8 blah 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 dt. Okay? And this will give me gamma of 5/4 minus x plus, now I have t to the 4, so it's t to the 5 over 5, so I will have x to the 5 over 5, and so on and so forth. Okay, this is the expansion as x goes to 0. Okay, now I would like to consider, not fully consider, but partially consider a special case that will be important later on. And this is the incomplete gamma function. So by definition, the gamma function of, how do you want to write it, of a is the integral from 0 to infinity of t to the a minus 1 e to the minus t dt. Right? That's a gamma function. And by the way, do you remember how the, right, if I'm plotting gamma of x as a function of x, not x, gamma of a, right, as a function of a, how does it look like? So the gamma function has a singularity when a is 0. Then it goes down, and then it goes up asymptotically. Here it's like a factorial. Okay? Now, here it has a jump. So at 0 it is doing like that, and it diverges again where? When a is minus 1. Then it reappears from here and goes down and diverges at a equals minus 2. And so on. So the gamma function diverges in every negative or 0 integer a, and otherwise the gamma function is well defined. Now, let's pick for the moment, okay, so this is the gamma function. Now I would like to consider the incomplete gamma function, which is gamma of a and x, and is defined as the integral from x to infinity of t to the a minus 1 e to the minus t dt. Right? I want to approximate the incomplete gamma function at the limit x goes to 0. What is the asymptotic of the incomplete gamma function when x approaches very small values? Okay? Okay. So what are we going to see here? Let's assume for the moment, let's assume that a is larger than 0. If a is larger than 0, I can split the gamma function the same way, this incomplete gamma function, to the integral from 0 to infinity of t to the a minus 1 e to the minus t dt, minus the integral from 0 to x of t to the a minus 1 e to the minus t dt. You see? That's very simple. Now, the first integral is what? Is a complete gamma function. Right? There is no... So I have gamma of a minus, so now because x is small, I can expand the t in Taylor series. So I can write this as sum from n equals 0 to infinity of minus 1 to the power of n divided by n factorial, and then I have t to the power of a plus n minus 1. Am I right? Integral from 0 to x. Right? The t to the n is this, is the exponent, and the t to the a minus 1 is here. And this is solvable, so what I have is gamma of a minus sum from n equals 0 to infinity of minus 1 to the power of n, x to the power of a plus n divided by n factorial times a plus n. After the integration. Okay? Good. So this is asymptotic of the incomplete gamma function when a is positive, provided for x very small x. The x goes to 0 asymptotics of the incomplete gamma function. Now, what will happen if I will take the a negative case? Suppose a is minus 1/2.
You cannot exchange the sum and the integral
Why?
because you have divergences.
Yes. If a is, say, minus 1/2, then here if I'm taking n 1/2, n0 for example, then I have t to the minus 3/2, and this is an integral that diverges at the lower bound. You see? See the problem? So it's quite complicated, we can spend half an hour to explain it. But for the moment, I would like you to, I mean, you can find it in the book, in the Holy Book of Mendel and Orsag. But although we obtain this for a larger than 0, it turns out that the same expansion is valid also when a is smaller than 0. Okay, so this is good also for a is smaller than 0. You do a lot of work and end up with the same expansion, okay, provided that
A is not an integer.
a is not negative integer, because then the gamma of a blows up. Right? So this works for a larger than 0 and a smaller than 0, provided that a is not 0, -1, -2, and so on. Are we okay? Please feel free to ask whatever questions you have. So what remains, and which is the most important case, is the incomplete gamma function when a is 0. Right? So for example, gamma of 0 and x is the integral from x to infinity of t to the -1 e to the minus t dt, right? And clearly you cannot calculate, I mean, this, when t is very small, e to the minus t is a constant, but you have integral over t to the -1, and this diverges logarithmically. So you can't do it like that. This procedure cannot be correct, because if I will replace this x by 0, I will get divergence. The only reason why this integral do not diverge is that x is not 0. Okay? So, what can we do? Okay, by the way, because this is very important, this is a very important function. It appears in many, many cases, in physics, also in mathematics. This is known also as the exponential integral. Right? It's another name for the same thing. The incomplete gamma function for negative integers and 0 is also known as an exponential integral. The only problem is that people are using different let me write it, e. People are using e1 of x is z. So this is the first exponential integral despite the 0 here. So you have to, e2 will be, right, e2 is gamma of -1 and x. And so on and so forth. So they start counting from here, right? This is 1, 2, 3, this way, right? Only, I don't know why. I guess it's kind of historical, I mean, somebody did that and it stays like that. So again, the question is how to calculate the exponential integral. Which is the same as, I mean, just another name for subclass of the incomplete gamma function. Okay. What can be done to calculate the exponential integral? what we can do. Okay, so let's speak about E1, as I said. So good. So as I said, E1 of x is by definition the integral from x to infinity of e to the minus t over t dt. Okay? And here is a trick. A trick that will solve some of the problems. Let's speak about let's take the derivative of this with respect to x. This is very simple, right? Because how do we take the derivative of a function with respect to x? How we are taking derivative with respect to the boundaries, we just plug in the boundaries, right? And this is lower bound, so it comes with a minus sign. So the E1 dx is simply minus e to the minus x over x. Very simple. Now we have to find what E1 is. So what E1 of x will be. Okay, now we want, as I said, we want the asymptotics of this as x goes to 0. Okay, so we can write this as minus 1 over x, or let's write it minus 1 over x times 1 minus x plus x squared over 2 minus x cubed over 6, which is, and so on, okay, which is 1 over x minus 1 over x plus 1 minus x squared over 2, and so on. And now we can integrate term by term to find that E1 of x is minus ln x, this is that, okay, plus x minus x cubed over, no, I did a mistake. This is x, because I have a 1 over x here. So this is x over 2, so this is x squared over 4, and so on. Okay. So if x is small, I have this expansion. What is the problem in what I did until now?
The line.
No, that's fine, because it tells you that when x goes to 0, the line diverges.
Wait,
this is good.
Where the line came from?
The line, the integral over 1 over x.
Oh, you integrate.
And you expect this function to diverge when x goes to 0. So fine, it diverges logarithmically. Now you know how it diverges. It diverges logarithmically. So still, if I want to use this, what's the problem?
Something about convergence, right? Convergence.
No, everything is fine.
Only true near 0.
Except that I did here something which is legal but not complete.
What? Exchanging some.
I took the derivative
You're missing a constant.
and I integrate. There is a constant of integration. So the question is, what is the constant of integration here? There is a C, constant of integration. What is the constant of integration? Again, there are tricky ways to show that. You can look at the book. I think that in the book they didn't do that by referring to a problem, to the problem sets where they ask you to do that, but
Which book is this? The vendors.
no, to the problem sets.
Yeah, from Bender.
Yes. So this is gamma Euler. What is gamma Euler? It's a constant, like E, like pi. It's a constant, 0.5772 or something like that, and it is defined as, interestingly, if you say gamma Euler is defined as the limit when n goes to infinity of the sum of 1 over n from n equals 1 to n minus ln n. see, integration over 1 over x is ln. But now you are not doing integration, you just sum over 1, 1/2, 1/3, 1/4, and so on to a very large number. This is very close to ln, but not ln, and the difference is defined as gamma Euler, which is again 0.5, I think 577 something. Euler constant. Good. Now, this was for E1. So E1 is a, remind you, E1 is gamma of 0 and x. Right? So this is how E1 looks like. But you want to know what, this is asymptotics of E1 as x goes to 0. Now we want the asymptotics of the other e's. Okay, so I can tell you that. It's, I mean, it's complicated expressions. Should I write it down on the blackboard or should I refer you to the book? At least we are going to need E2. So gamma of 1 and x, which is E2 of x. Again, the asymptotics as x goes to 0. So we have E2 of x, and this is
Gamma -1.
this is what? I have the formula, but the formula is complicated. The general formula, so I can write down the general formula and derive it from that. But maybe we can cut corners and.
Generally, you use the series definition of the incomplete.
Sorry.
Generally, we use the series definition that you wrote on the top board for the.
No. Okay, let me write it. Let me write the function in all its glory, and we will derive. You will tell me how to derive the specific one. So E n plus 1 of x, right, is maybe I can do the same trick. Should I? Yes. Okay. So at least. Okay. So E2 of x, I can write it as an integral from x to infinity of e to the minus t over t squared dt. Right? A is 1. Sorry, this is minus 1. Minus 1. A is minus 1, so I have t. Okay, now, so I can take the derivative. So dou E2, so x is simply e to the minus x over x squared, that I can write as 1 over x minus, do I have a minus here? Yes, because it comes from the lower bound. And so I have minus 1 over x squared times 1 minus x plus x squared over 2, say, which is, so I have, so what do I have? And I have to integrate. Wait. So I have minus 1 over x squared plus 1 over x minus
2.
Minus 1/2. Okay? Let's take another one. So we have minus x cubed over 6. So here we'll have plus x over 6. Integrating this one by one, I will get the integral of 1 minus x squared is what?
Minus 1 over x.
Is 1 over x. So I have 1 over x in a plus sign.
Yep.
Yes?
Plus 9.
Plus, no, the 1 over x is with a plus sign.
Yes.
Yes. Plus ln x. Minus x over 2 plus x squared over 12. Okay? And the only question is, what is the constant? So, okay, so I'll give you the formula for the constant of the n plus 1, exponential integral. And this is, so, for the n. And this is minus 1 to the power of n plus 1 over n factorial gamma Euler minus sum from n equals 1 to n capital N over 1 over n. Okay? So what will be C1 according to that? C1 is minus 1 to the power 2, which is plus 1,
Over 1.
divided by 1 is 1, so this is 1. And now I have gamma Euler minus
Just 1.
gamma Euler minus 1.
It means
No.
n minus 1 at the summation.
So what is going on? No, so this is perhaps must be. So we got gamma Euler minus 1, right? So this is C of n plus 1, I guess. So if n, wait. This is actually C2. So how to, C2 is gamma Euler minus 1, C1 is minus gamma Euler. So let's see. If I'm taking here n equals,
Maybe the sum starts at
no, this is, okay.
No, but
This is a 0. What should I do? Yes. If n is 0, okay, then I have minus 1 to the power of 0, which is 1. 0 factorial is 1. And I have, no, minus 1 to the power of 1 is minus 1, right? N factorial is 1, and I have minus gamma Euler, right? So this is so what should I do? I should put here again, when I put here n equals 0, I will get C1. So this is n plus 1. Yes. Okay. So here the constants are gamma Euler minus 1 plus blah blah blah. I don't like the fact that we have a plus 1 over x and plus ln x, but apparently this is what we obtained, right? We have a minus here, and the integral over minus 1 over x squared is, yes, apparently this is true. right? And essentially, so now you can calculate whatever you like, right? E3, you do this trick and find out all the terms except of the constant, and from this formula, you can find what the constant is. Yes?
You don't like it because of the divergence at x equals 0? Because you have this one going this way, this one going this way? Or like what reason should I reject it?
No. The divergence at x, this is nice because it tells you that here, at 0, it diverges logarithmically. At -1, it diverges like 1 over x. At -2, not 1 over x, 1 over x minus 1. Yes? At -2, it diverges like 1 over x squared and so on and so forth, which is fine because this is completely fine with the integral. Because you have an integral, yes, of 1 over t to the m e to the minus t dt. Now you can, close to 0, you can neglect it, right? So you have t to the minus 1. That's a divergence. This is fine. I simply, for some reason, I don't like the fact that you have here plus and plus, but I think that it came from this derivative. Okay. So this is quite important to. Who was the guy that obtained the tables for E for the exponential? Very useful piece of knowledge that has nothing to do with math, but just with technicalities. If you are using Mathematica and MATLAB, they have different definition of the exponential integral. Okay, and differing by minus and something, and I mean, take care. If you want to if you calculate something in Mathematica and it gives you exponential integral, you want to plot it with MATLAB, be careful because they have different definitions. It's always confusing. I think that what I did here is a MATLAB one, and the Mathematica thing is more complicated. I mean, it's less trivial to me, but this is what they did, I guess, based on some former mathematical literature. I've forgotten the name of the guy. Okay. Anyhow, so after doing that, let's try to implement these functions, these asymptotics, right? So these are the asymptotics of the exponential integrals in the relevant and in general of the gamma function. And now let's implement it to do something really tricky, which is solution of integrals by asymptotic matching. So we implemented asymptotic matching in boundary layer theory and then in WKB. Now let's implement it to find a solution for an integral. So the integral I would like to consider is the integral from 0 to infinity of e to the minus t minus epsilon over t dt, as epsilon goes to 0. Okay, now, how the integrand look like? It's always a good advice when you try to say something about the integral to think about the integrand and how it looks like. So this is e to the minus t minus epsilon over t as a function of t. How this beast behaves.
Just you start with the e to the minus t. Just looks like
So if you have only e to the minus t, if you have only e to the minus t, it will go like that. Right? If I'm taking epsilon to be 0, then I have this black dashed line. Okay? However, so if epsilon is small, when the, yes, exactly. So when the actual function will deviate from the dashed black line,
Near 0.
if epsilon is very small, only when t is even smaller than epsilon. And in this case, it will go when if t is much smaller than epsilon, then I have here a huge number, and it will go to 0. So I have something like that, where this is essentially epsilon, more or less. Okay? So our goal, clearly when epsilon is going to 0, the smaller epsilon is, we are going to have something like that, and clearly the integral over e to the minus t. What is the integral from 0 to infinity on e to the minus t? 1. So the integral will approach 1 as epsilon goes to 0, but the question is how? You see? Good. So, and here is a very interesting trick that we didn't implement it until now. The trick is to define a parameter delta just that satisfies, because epsilon is going to 0, so we can always find delta that will satisfy delta is on the one hand much smaller than 1, and on the other hand much larger than epsilon. So for example, if you want a concrete example, maybe delta is going like square root of epsilon. At epsilon goes to 0, delta will be much larger than epsilon, but otherwise it's a free parameter. And the trick we are going to do is to split this integral into two integrals. Integral from 0 to delta of e to the minus t minus epsilon over t dt, plus integral from delta to infinity of e to the minus t minus epsilon over t dt. Okay? Let's define them as integral number 1 and integral number 2. You agree that this is perfectly legal, what I did? The only question is what it is good for. Okay? So, we will treat these two integrals differently. I mean, each one according to the approximation that is valid for a given integral. However, after when the smoke clears up at the end of the day, we should find that delta disappeared from the answer. The answer should be delta independent. And this is a very strong constraint that will make us, that we have to satisfy.
So
right?
the delta terms have to cancel out.
All the delta terms, if you want to calculate to first order in epsilon, right? Then all the delta terms should cancel out, but not all the delta terms. All the delta terms that give you something that is larger than epsilon.
Okay.
So epsilon delta, I think that epsilon delta should not, but epsilon should, or delta by itself should. And this is a very, if you make a mistake, you immediately find it, because then the deltas are not going to disappear.
That's nice.
Yeah, it gives you a self-control on mistakes, which is kind of a useful thing. Okay, so let's start with integral number 1. Integral number 1, or should I start from 1 or from 2? No, I would like to start from integral number 2. So in integral number 2, I am in the, say, outer regime here. This is the regime of integral number 2. This is where we are doing integral number 1. Okay? So in the regime of integral number 2, t is much larger than epsilon. Right? In this regime, t is much larger than epsilon by definition, because t is much larger than it start with delta, the lower bound, and delta is much larger than epsilon. Okay? So this term, e to the minus epsilon over t, is e to the minus schmutz. Okay? So we can write it, integral number 2, as an integral from delta to infinity of over e to the minus t times 1 minus epsilon over t plus 1/2 epsilon squared over t squared, and so on. You see? Okay? Now we would like to do it term by term. Okay? So what we find is that the first integral is the integral from delta to infinity, e to the minus t. So we have integral over, okay, let's do it here. We have delta infinity minus e to the minus t, only the first thing. And this will give me simply e to the minus delta. Okay? But because delta is small, and I would like to keep only the relevant terms, I will replace it with 1 minus delta. So this is e to the minus delta, and I would like to replace it by 1 minus delta. If I want higher orders, then I can write delta squared over 2, and so on and so forth. But I can assume that delta is, I don't know, some power of epsilon, that such a delta squared is already smaller than epsilon. Okay? So I'm keeping only I will keep only the first order. Now, the next term is minus epsilon times the integral from delta to infinity over e to the minus t over t. Now, what is that?
E1.
Incidentally, we already, right? So, incidentally, what we have here is e times E1 of delta. What will be the next term? Plus 1/2 epsilon squared E2 of delta, and so on. Good. This is integral number 2. What about integral number 1? So integral number 1 is delta is much smaller than 1. Now I'm using the other. What I implemented until now is that delta is much larger than epsilon. Now if delta is much smaller than 1, I can expand not this but that. So I can write it as the integral from 0 to delta over e to the minus epsilon over t times 1 minus t plus t squared over 2, and so on. dt. So in regime number 2, I expanded the epsilon over t, e to the minus epsilon over t. Here I am expanding the e to the minus t, because now t is small. But epsilon over t may be very large. Okay. Now I would like to change variables. So I would like to define, say, q is epsilon over t. Right? So t is epsilon over q, and dt is epsilon over q squared with a minus. So I would like to write the integral over dq over, so I have minus epsilon here in front of the integral, minus epsilon, integral over dq over q squared. Now what about the boundaries?
Infinity.
So the 0 is becoming infinity, okay? And what is the lower bound here?
Epsilon over.
Because you said that delta is square root epsilon, and you just get delta again.
No, I'm keeping
Epsilon
delta as a
over
free parameter.
1 over
Epsilon over
delta.
So this will be here. This will be again. Q is epsilon over t. Now if t is delta, then I have epsilon over delta.
But square root is actually a really good choice because then
And I can take this minus out because I exchange the boundaries. And now I have e to the minus q. You see? And here I have 1 minus t. T is epsilon over q plus 1/2 epsilon squared over q squared, This was just a change of variables, nothing more. Okay, so what is the result?
same thing as this
The
one.
same.
Maybe you
To
can
the
do
leading order in epsilon, I will get epsilon times what?
E2 or E squared. That's E2.
There is something I don't like here. E. Yes. Times E2 of what?
Epsilon over delta.
Of epsilon over delta. Now, is epsilon over delta small?
No, it's not.
Yes.
Yes.
Oh.
Yes. Yes. And then the next term will be minus epsilon squared, if you like, times E3 of epsilon over delta, and so on and so forth. Okay. So we have the integral 1, and we have integral 2, and now we want to collect all terms that are order up to order epsilon. Right? Or, okay, in a moment I will explain it better. So what do I have here? Maybe I can erase this. Let's start. From integral number 2, I have 1 minus delta, right? Minus epsilon times E1. So plus epsilon gamma Euler. You see? Plus epsilon gamma Euler. Plus epsilon ln delta. Ln delta is large because delta is going to 0. Right? You see? What's the next thing?
Minus epsilon delta.
Minus epsilon delta. And the next thing will be plus epsilon delta squared over 4. I think that maybe also this. I will let's see, right? Okay. Now what about the next? The next thing is going like 1/2 epsilon squared, and I don't have anything. Okay, so I can always neglect the next thing to first order an epsilon. Now what about integral number 1? Integral number 1 gives me epsilon times E2. So it gives me epsilon times gamma Euler minus epsilon plus, okay, now I have epsilon times 1 over x, but x is epsilon over delta. So 1 over x is delta over epsilon. So epsilon times 1 over x is simply delta. Next term is plus epsilon, and now I have ln of epsilon over delta. So I will write it as epsilon ln epsilon minus epsilon ln delta. And the next term will be minus epsilon, again, x is epsilon over delta, so the next term will be epsilon squared over 4 delta, I guess. Okay? Now, what's happened if I add these two terms?
The delta.
So, this delta cancels with this delta, and this dangerous term, epsilon ln delta, because delta goes to 0, so ln delta is huge, but it cancels with that.
And the final term.
Okay? And
The final term.
and what else?
The epsilon gamma become combines to simplify.
Yes. Okay. So up to and all these terms, this one, and this one are smaller than order epsilon.
When you did the e to the minus delta, you stopped at 1 minus delta. You did like first order, right? The first term in the second equation.
Well, sorry.
The first term.
You are speaking about integral 1 or integral 2?
Integral 2, the summation you just did. Why did you stop at e to the minus delta, the first term that you did 1 minus delta for? Why did you stop at like the order of O delta?
Because I can take delta, so I can take delta to be, say, okay, I've erased it, but all I need is delta to be much larger than epsilon, much smaller than 1. So suppose I am taking delta to be epsilon to the power of 2/3.
Okay, so now
So now delta squared is lower order than epsilon.
Is there such a concept of like as close as
Yes,
you want? As
you can do it as close as you want. In the limit epsilon goes to 0.
Okay, cool.
You still have infinite. So these three terms are negligible. Okay? And what remains is that the asymptotics of the integral that we started with is 1, as expected. And now we have plus 2 gamma Euler minus 1 epsilon. These are, the one is this, and that. Give me 2 gamma Euler minus 1 epsilon. And we have a non-trivial contribution, which is actually much larger than epsilon. And this is epsilon and epsilon. Because when epsilon goes to 0,
This is huge.
this is huge. I mean, the ln epsilon is huge. This is still going to 0 when epsilon goes to 0. But the ln is much more than 2. Actually, 2 gamma Euler minus 1 is almost 0. But this is just an incidence, right? That gamma Euler is close to 0.5. So 0.577. So you have this is 0.14 order of magnitude, 0.5, and this is this as epsilon goes to 0. This is much larger than that. Okay. So the non-trivial thing is to get this, which is not by any means you can't. I mean, you understand that you can't get it from just parallel expansion because it's not a parallel. You have a LAN here, and that's it. And now that you are such experts, then I can, in the exam, I can give the second order to calculate up to epsilon squared. Okay, good. So this is, I think, a fascinating example of using the method of asymptotic matching to integrals, to the estimation of asymptotic behavior of integrals. Okay, fine. So what we did until now, we were just expanding the integrand or the boundaries, and we did asymptotic matching based on these formulas for the incomplete gamma functions that I think worth mentioning because at least I encounter them many times in a whole lot of physical problems. At least I don't know exactly what type of physical problems leads to these expressions, but you can find gamma Euler appears. Sometimes people are even using it as an indication that they are doing the right thing. I mean, if you get gamma Euler, it implies that you're doing something good. Good. Now, next, I would like to speak about doing the asymptotics of integrals using integration by parts. So integration by parts, you all know that the integral of u dv is the boundaries of uv minus the integral of v du. Yes? I think you learn it in high school, right? It's not a university thing. I'm so far away from this that I don't remember exactly.
We have this rule they taught us, gzor ushmor, ushmor ugzor. It's like a way to remember it. Because if you move this to the side, you get udv plus vdu.
What?
זה חוק שאמרו שמתמטיקה מצליחים כאילו UTV.
נראה לי יותר מבלבל מ... אבל טוב, אוקיי.
זוכר את זה עד היום.
I just remember the reverse product rule, that's it.
So, okay, so our goal here is not to learn how to do integration by parts, but how to implement integration by parts as a tool for in asymptotic analysis. And to begin with, let's start with an integral that we already begin with this lecture. So I'm speaking about the integral from x to infinity of e to the minus t to the power of 4 dt. But now I want to asymptotics of this integral as x goes to infinity. Not as x goes to 0, but as x goes to infinity. Okay? What is the trick? The trick here is to write this integral as the integral from x to infinity of d dt e to the minus t to the power of 4 dt. Now, d dt e to the minus t to the power of 4 will give me minus 4t cubed in the parallel term. So I have to derive. right? Okay, this is just an algebraic manipulation. Same thing. Okay, why this algebraic manipulation is useful? Because now I can define this as u and this as dv, and I will claim that this is equal to minus x to infinity over e to the minus t to the 4 over 4t cubed plus the integral from x to infinity of, okay, now I have to take the derivative of this, and the derivative of this will give me another minus, I guess, and I have to take the derivative of t, so I will have 3 quarters t to the 4 e to the minus t to the 4 dt. Do you agree with me?
Did I? Yes. Okay.
So, what I obtained is, what I obtained here, the upper bound of course gives me nothing. So I have only the lower bound. So this kills a minus. And I'm getting e to the minus x to the 4 over 4x cubed. Minus the integral from x to infinity on of 3 quarters e to the minus t to the 4 over t to the 4 dt. Now, I would like to claim that this term is the leading order in the asymptotics of this integral. Right? In order to claim, to convince you, what I should do is to convince you, in order to convince you in my claim, I have to convince you that this term is negligible with respect to this term as x goes to infinity. Okay? How do I do that? I would like to claim that this term is much smaller than 3 over 4x to the 4 integral from x to infinity of e to the minus t to the 4 dt. Do you agree? Why this is true?
Because you're only comparing it with the other.
No, I'm saying that this term is much smaller than this one. Why? It's smaller. Okay. This is an upper bound for that. Why?
Because t to the 4.
Because you take down the t.
Here, t to the 4 is always larger than x. Than x to the 4. So taking x to the 4 outside is an upper, is clearly an upper bound. So this is clearly an upper bound of that. But here you have 1 over x to the 4 times the integral we started with, and when x goes to infinity, this will be negligible. Right? So you see that this contribution, whatever it is, will go down like 1 over x to the 4, whereas this one is going down like 1 over x to the 3. Right? So at least 1 over x to the 4. And actually you can continue now. You can take this, integrate by part again, and get the second term and the third term and so on and so forth, and it works. So this is asymptotically, this I is asymptotic to e to the minus x to the 4 over 4x cubed as x goes to infinity. Okay? Any questions? No. So, if there are no questions, let's do another problem. let's calculate okay. Can we calculate the asymptotic of this as x goes to infinity? X goes to infinity, yes. Sorry. Can I do that using integration by parts?
Isn't it just an incomplete gamma function?
Oh, this is not exactly because it's from the upper bound, but
So you do gamma minus.
okay. The point is that if we are trying to do that using integration by parts, okay, so we will define this as no, we have to write it as yes. So integration by parts, I can write it as integral from 0 to x of 1 over square root of t d dt of e to the minus t minus, because the d dt is doing nothing but giving me a minus. So I is exactly that. And now I can use the integration by parts to have minus 0 to x of e to the minus t over square root of t plus integral from 0 to x of e to the minus t, and now I have to take the derivative of t to the minus 1/2, so it will give me minus, and I will have 1/2, and I will have here t to the 3/2 dt. Right? And this is problematic. Why it's problematic?
Because at 0 it's
Because I cannot plug the 0 here, it will diverge. So at least a naive implementation of integration by parts is not working. Okay? However, I can do a trick and then use the integration by parts. Okay, this was a naive implementation that fails. But what I can do is to write this as the integral from 0 to infinity of 1 over square root of t e to the minus t dt minus the integral from x to infinity of 1 over square root of t e to the minus t dt. Right? Now, what is the first integral?
that's a gamma.
That's a gamma of 1/2. So this is a gamma of 1/2.
It's square root.
And now I can implement the integration by part to this, because now I don't have the 0. Right? So I can write it as this. I mean, the only thing I have to change is the limits, boundaries. So x infinity, and this is x and this is infinity. Right? And this is x and this is infinity. So to the leading order, I will get what? No.
Minus 1 over square root of
Yes, because I'm getting from the lower bound here, so I should switch the minus to plus. So I get minus e to the minus x over square root of x. Yes. Okay. Now,
Wait, did the whole integral vanishes?
sorry?
The whole integral vanishes? You have e to the minus x over x from the top, from the bottom boundary of the x of the
No, if x goes to infinity, you have gamma of 1/2.
Yeah, but there's the term integral from x to infinity of 1 over of the e to the minus t to the 3/2.
The next term.
Yeah, the next term will you can do now the same trick of integration by parts, because you don't have divergences from 0, and it will give you the next term will be no, I didn't write it, so you have to do that. But
So this is a satisfactory solution.
yeah, this is a leading correction to gamma of 1/2 as x goes to infinity.
How do I know there's not a square root of x term in the integral?
What?
How
In
do
the
I-
next integral? Because this is going to like t to the 3/2, and you can again bound it from above
Okay.
by taking x to the 3/2 here.
Okay.
So it will not be smaller than, I mean,
Won't
you
be
can
square
show
roots.
that the next correction is not same trick. Okay. Last example. Last example. I want to calculate, again x goes to infinity, I want to calculate the integral from 0 to x of e to the t squared dt. Not minus t squared, t squared, right? Now, I leave it for you to check that the tricks we presented until now are not going to work, right? Because if we will replace it by, we cannot have the x from 0 to infinity. If we try to do a naive integration by parts, we will get something that diverges at 0 and so on and so forth. So the trick now is to write this integral, again, as a sum of two integrals. One of them from 0 to a, and the other one is from a to infinity. Okay? Well, I assume that a is much smaller than 1. Right?
From a to infinity or from x?
From a to x. Sorry. From a to x. Okay? Now, this integral may be written as an integral from 0 to a of 1 plus t squared minus t to the 4th power over 2 blah 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 blah, and so it will be 0a, and I have here t plus all of them are plus t cubed over 3. What I did it? Yes, plus t fifth over 10 and so on, t fifth over 10, yes, and so on and so forth, right? And it will give me, I will put the upper bound, so I will have a plus a cubed over 3 plus a to the 5 over 10, and so on and so forth. What is important is, okay, I did a mistake? What's important is that everything is proportional to a. And if x goes to infinity, all these terms are going to be subdominants. Right? So all this integral is actually garbage. It has no contribution to the asymptotic behavior of that integral. Okay? And now here I can implement the integration by parts. Because now I can write this as the integral from a to x of d dt of e to the t squared 1 over 2t with no mic. 1 over 2t. Is there a minus sign here?
No.
No. Okay. And this will be equal to a x of e to the t squared over 2t minus integral from a to a plus of 1 over 2t squared e to the t squared. Right? And now I can plug the x, which is the only important thing. So the leading order will be e to the x squared over 2x. Right, this will be the leading order. All the a terms are not really important. Yes. Okay. Now, okay, I will stop here. I owe you, I guess, some 10 minutes or so from last former lectures, so this will be part of the paying my debt. And next time we are going to I am going to present to you the most, I guess, the most useful. It's one of the most useful tricks that are in terms of implementability that I'm going to present in this that I presented in this course, and this is Laplace integrals. So that's for next time. Very useful. By the way, are all of you students of Eli Barkai, just for curiosity? No.
Only me.
Only you?
Yeah.
Ah. And you? And others?
Is this a required course for
I am.
Eli?
I am.
קורס דרוש לאלי ברקאי?
You are also with Eli?
Yeah.
Okay, 3 of you.
למה?
מה?
למה? סתם.
סתם לא, פתאום סקרן אותי, בעצם... אז עם מי עובדים היתר?
אני עם דמיטרי. דמיטרי
אה.
גוטמן.
דימיטרי.
יונתן.
אתה עם יונתן? כן, נכון, אני רואה אתכם תמיד הבעיה שלי זה שהזיכרון שלי לשמות ופרצופים הוא נורא והיום. אני רואה אנשים בהקשרים שונים, הם לא מתחברים אצלי לדמות אחת. היה פה פעם שהלכתי במסדרון והלכו איזה 2 דוקטורנטיות, פתאום ראיתי אותם ביחד וקלטתי שהם לא אותה אחת. שנים חשבתי שהם אותה אחת, באמת. לא... אז אוקיי, אתה?
אני לא, אני תואר ראשון.
אתה... הבנתי. אז אני באמת, אני רואה אותך בקורס בנומרית, או שזה רק הולוגרמה שלך?
לא,
זה אתה. אתה רואה? אתה לא מתחבר לי ב... אתה אמרת... ואתה?
אברהם קליין.
אוקיי. טוב, אוקיי, אנשים רציניים. יפה. אז...
בקשר למבחן.
כן.
יש דף מסחר.
נדמה לי שלא.
אנחנו מכינים אותו מביא או שאין בכלל.
נדמה לי שאין בכלל. אני אבדוק עד כמה שאני זוכר אין בכלל.
במבחני עבר?
מבחני עבר שלחתי, מישהו פה ביקש ממני.
אתה יכול לשלוח לנו בלומדה? זה מה שעשינו.
אוקיי, בסדר. שמישהו מכם ישלח לי איזה אימייל, כי אני כבר בימים האחרונים אני שכחתי, אני מתחיל לשכוח גם דברים טריוויאליים, משהו לא ברור. אני מקווה שזה לא הגיל, אלא בעיות אחרות. אז תשלחו לי איזה אימייל ואני אדאג שהמתרגל יעלה לכם, או מה שלא יהיה. מישהו ביקש ממני, מישהו פנה אליי, וביקש ממני מבחנים משנים קודמות ושלחתי לו לפני איזה שבוע, אבל בסדר.
כמה שלא תהיה במבחן.
מה?
כמה שלא תהיה במבחן.
מה זה?
כמה שלא תהיה במבחן.
נדמה לי 3 שאלות.
3, אוקיי.
כן.
רגע, אין דף נוסחה?
נדמה לי שלא.
אני חושב על דברים שכתבת לנו כאן בתור כזה, קחו את זה בתור כלל ברזל. נגיד הקבוע אינטגרציה של גמא n, שאמרת שזה כאילו.
Hello everyone, today we're gonna see asymptotics of integrals, and we'll use Laplace method and the integration by parts to calculate the integrals. So first of all, let me write some theory. So Laplace method is, so we will use it for integrals with the special form. So, and this basically works for, this method works then x goes to infinity. So we have a big parameter here, and that's why we can approximate this integral by taking the maximum value of this function in the exponent. Okay, and there are several cases. So the first case is then function phi has a maximum at point C, and C is inside the interval. So it's not like A or B, it's some value inside the interval. And the second derivative of phi is negative. So in this case we can approximate this integral using the following formula. Okay, that's the first case. Second case is then function phi.
It's phi c.
Phi of c, where c is maximum point. Okay. So yeah, case 2 then phi of t has a maximum at B at point A or B, or at the endpoints. In this case, plus integral is approximately minus f of A. So in this case, I'm writing it for t equals A. Okay, but in case of B, we just need to change all of it. Change from A to B. So x phi prime of A times e to the x phi of A. Okay, and the last case, then phi t has a maximum at t equals A, and phi of A, phi prime of A equals 0. So then the function phi has a sort of a global maximum, local maximum at this point. In this case, plus an integral, approximately half square root of pi minus x phi double prime of A f of A e to the x phi of A. Yeah, there is also f of c in this formula. Okay. So the only difference is in this 1/2 coefficient.
What's the difference between case 2 and case 3?
So in this case, because of
Does it has a max of t equals a or b, and then case 3 is it has a max of t.
for example, you have integral from 0 to 1, and there is minus x sine t dt. So phi of t in this case is minus sine t, right? Where is the maximum from 1 to 0, this function? Obviously at t equals 0. Okay? You see? And at this point, the derivative of phi is not 0. So it's like it's not the global maximum of the function, but it's
not
just
a local maximum, but it's a maximum of the domain that we've
Yeah.
established. Okay.
Yeah, because of the
domain.
domain. Because
So
of
we
the
say in the case 2 that phi type is not 0.
So just because of the domain. Yeah. Okay.
And the third case is also for B. That's good.
Yeah, for B it's the same with the just change A to B.
Okay.
So let's solve a couple problems. The first one is the asymptotics for incomplete gamma function from x to infinity t minus t as x goes to infinity. So here we don't actually need to use the plus method because we can simply integrate it by parts, right? So when I do first integration by parts, I'll have minus t to the power a minus 1 times e to the minus t from x to infinity, and plus integral a minus 1 t to the power a minus 2 e to the minus t dt from x to infinity. So the upper on the upper boundary we have 0, and on the lower boundary we have x to the power a minus 1 e to the minus x. Okay, then plus this integral, and we'll do again integration by parts, and we'll have minus a minus 1 t to the a minus 2 e to the minus t from x to infinity, then plus integral a minus 1 times a minus 2 t to the a minus 3 e to the minus t dt. Okay, again, here is this equals 0, and the lower boundary is x to the a minus 2 times e to the minus x. So basically we can write it as x to the a minus 1 times e to the x multiplied by 1 plus a minus 1 divided by x, then plus a minus 1 times a minus 2 divided by x squared, and so on and so forth. This is the expansion. Okay. So, second example, we need to evaluate this integral. Again, for the case then x goes to infinity. Okay. This is the plus integral, right? And it's the case 2, right? Because phi of t here is minus sine t. Okay, the maximum here is at t equals 0, so phi prime t is minus cosine t. Okay, and using this formula, we can write that this integral asymptotic to, so minus function here is 1, so e to the x times phi at 0, which is 0, divided by x times the derivative at 0, so it's minus 1. Yeah, that's it. So it's just minus 1 over x, the asymptotics. Okay. So the next one, f(x) is from 0 to 1, and e to the x t minus t squared dt. Okay. Here is phi of t is t minus t squared. So to find the maximum, take the derivative, and it's 1 minus 2t. Makes it equal to 0, and t is 1/2. So this point is inside the equation domain. So let's calculate the integral, right? So it's case 1. Okay. It's 2 pi minus x times the second derivative is minus 2. Okay, then the function here is 1, e to the x times 1/2 minus 1/4, so it's 1/4. Okay, so the asymptotics is square root of pi over x times exponent to the x over 4. Okay. The next one. Again, we need to find the asymptotics for gamma function. And then as x goes to infinity. Okay. So basically we'll derive this Stirling's formula. Okay. And we want to use the plus method. Okay, so but we don't have here an integral like this. So what we're going to do is we will write this t as e to the x ln t. Okay, so basically we'll use the definition of what is 1. And then in the integral, we'll have e to the x ln t minus t over x dt. But the problem is that we have, so to say, maximum of this function that depends on x, right? Within maximum. So that's why we need to change variables in the integral, right? And we can use substitution, for example, s equals t over x, okay? And then dt is just x times ds, right? So it's e to the x ln t is s times x, so I can write it as a sum of lns. Then minus s d, so x here, ds. And now x times ln x is just a constant, right? Because we're integrating over s. So that's why I can move it from the integral. And the x e to the x times ln x is x to the x. And here I have one more x, so it will be x to the s plus 1. Exactly. So, and the inside the integral, I have x times ln s minus s ds. Okay, now this is my phi. Phi of s ln s minus s. I want to find the maximum of this. So it's 1 over s minus 1 equals 0. So maximum at point s equals 1, which is inside the domain. Okay, therefore this is the first case. Okay. And the second derivative is minus 1 over s squared, which is at this point negative. So x times x to the power x plus 1, then square root of 2 pi divided by minus x times the second derivative at s equals 1, so divided by x times e to the x, and phi at s equals 1 is minus 1, so e to the minus x. And this is exactly the formula for the asymptotics for the gamma function, or asymptotics to factorial for big n. It's student's formula. Okay. Next one. We have to evaluate integral from 0 to infinity, e to the minus x, hyperbolic sine, square of t, dt. So our function phi of t is minus hyperbolic sine square of t, phi prime of t is minus 2 hyperbolic sine of t times hyperbolic cosine of t. So the function has maximum at t equals 0, right? And it's this point, right? So at the lowest boundary of the integral, that's why it's the case free. Yeah, case free. So phi double prime of t is minus 2. There is a cosine, hyperbolic cosine square of t plus hyperbolic sine square of t. Okay, and at this point, it's minus 2. So that's why the asymptotics of this integral is 1/2 square root of 2 pi divided by minus x times this. So technically just square root of pi over x times e to the x and the function at this point, which is 0. So just this.
As x goes to infinity.
Yeah, all of this only then as goes to infinity. Okay, the next one, number 6. Something more interesting than that. Integral from 0 to infinity e to the minus xt. Here is sine of square root of t divided by square root of t dt. Okay. So in this case, we will use the Taylor expansion of this. Okay. So let's do it. Infinity. We have t to the minus 1/2 e to the minus x times t, and the expansion of sine. Okay, times t to the power 2n plus 1 dt. Okay, so I just expand the sign.
Should this be square root of
Yeah,
2 to the n plus 1 over 2?
It's here.
No, but also the sign, also for the, because there's also square root in, for the t
Okay.
and the sign.
That was better. Thanks. So then I can combine this and this, right? And I'll have minus 1 plus 1 here t to the n e to the minus x t, and we're almost there, right? We will convert it to the gamma function, right? But before that, we need to make sure that we have the same variables here and here, right? So to have it, we need to multiply here by x, right, and here by x. So in total, we multiply by x to the n plus 1, and therefore we need to divide by it, right? So x to the n plus 1. Great. And then sum over n from 0 to infinity minus 1 to n. Here is gamma of n plus 1 divided by 2 n plus 1 factorial times x to the n plus 1. Okay, again, this is the expansion, then x goes to infinity. Okay, the next one, integral x 0 to infinity e to the minus x t square root of t times 1 plus t to the minus 1 dt. Okay, here we'll do pretty much the same. We'll expand this. It's just a geometrical series, right? So you can write it as a sum from 0 to infinity. There's a minus 1 to the n, integral from 0 to infinity. So here we have t to the 1/2, and here will be t to the n. So this is the n plus 1/2 e to the minus x t dt. And again, we will convert it into gamma function. So I multiply this and this. So in total, I need to divide it by x to the n plus 3/2. Okay. And this is gamma of n plus 3/2. So the asymptotic expansion is sum over n from 0 to infinity minus 1 to the n gamma of n plus 3/2 divided by x to the n plus 3/2. Okay, that's the answer. So the next one, example number 8, we have integral of x from 0 to infinity e to the minus x times t to the 4th dt. Okay, and in this case, phi of t is minus t to the 4th. And we see that all derivatives up to third one will be 0 at the maximum. So that's why we cannot really use case, because it's 0, it case 2, right? So because the first derivative is 0, right? And we have to change the variable, and basically we will convert it into gamma function. We don't even need to use the plus method here. So we'll use, let's call it S. S is x times t to the 4th, right? Then ds is x 4x times t cubed dt, and then dt is 1 over 4x times t cubed ds, and then t cubed is x over s over x to the power 3 over 4. So, well, we here just minus s, and dt will change by this. So it's 1 over 4, and x will be to the 1/4, right? Like this, I think. Here we have s to the minus 3 over 4, the s. This is gamma of 1 over 4. Yeah, that's exact solution, not even the expansion. Okay, so in the third notes I have pretty much the same example for the t cubed. So it's not very informative for us because pretty much the same way to solve it. And the last example is the following. So integral x from x to infinity e to the minus t divided by 1 plus t squared dt. Again, as x goes to infinity. So we'll try integration by parts. Okay. So it's minus e to the minus t, 1 plus t squared, and plus integral from x to infinity to t e to the minus t 1 plus t squared squared dt. I think the minus sign. So minus from here, minus. So 3 minuses will give us minus here. Okay, and then we plug in the boundaries. We'll have e to the minus x divided by 1 plus x squared minus integral from x to infinity to t e to the minus t 1 plus t squared all of the square dt. So and we can compare the high terms from expansion of this. Again, we will integrate it by parts, and if we compare it with this term, we will see that they are smaller. So basically, if we want to take more terms, we'll just continue to expand it. This is the leading order of the expansion. Okay, so that's it for today. Next week we will see the integrals. Basically, we'll see plus integrals, but with the complex function phi. So we will use a method of steepest descent, and basically that will be the last tutorial and the last lecture next week. Yeah.
You have uploaded homework 10, I think. It's like in the power pole and oscillators. It's optional or
Homework 10?
yes.
No, it's multiple scale analysis.
About the oscillation differential equation.
Yeah. It's not the last
Because
one.
in the lecture we didn't cover all this stuff.
I think you did. I mean,
Oh,
then
yeah, I wasn't here.
yeah, probably you missed the lecture.
I multiply scale משהו?
Yeah.
maybe.
Layer?
Nadav call it the double
Double.
perturbation theory. Double times.
Two times
perturbation.
perturbation theory.
Yeah,
Two times
two times
anticipation,
perturbation.
yes.
No,
But in the
this
book
lecture
it's
I was here.
multiple scale.
This lecture I was in.
Yeah, and the homework done is about it. It's
I will check it out.
okay. So yeah, and on this tutorial we'll have homework 11, but integrals they're not scary at all. So you know all of this, and
There will be another homework?
another
What
homework,
else?
homework 11, and homework 12.
Oh.
But I mean, there are like four integrals. They like you will easily solve it, so don't worry.
No, we want them to...
It's
It will take 1 hour to solve it
for
maximum.
my-
So
Nadav
Yeah.
Barza.
Okay. Again, we asked Nadav to put the last year exams in the Moodle. Can you help
Vanderpool oscillator.
put him?
okay, I need to ask him because I don't have the last. I mean, he sent me some of them, but before I upload something, I need to consult with him. So
Okay. Thanks.
okay, if you don't have any questions,
I
See you next week.
question.
okay.
Do you know what it is?
Okay. Yeah.
When you do something like that.
Mhm. Yeah.
Bye. Thanks.
Bye bye.
Why it's correct? You have here what you don't change anything here,
Yeah.
but it's the power of n and the xt and
Yeah.
why it's right.
Because what is integration? Integration is the linear operation, right? So
Okay.
if I have like alpha f of x dx,
Okay.
I can put alpha inside or outside, it's just a constant, right? So because